Okay, so now we're ready to finish the proof. We have one last lemma to show, what I call it a theorem, to finish the proof of completeness. So we need to show that if sigma is a consistent set of sentences, then there exists a tau is an extension of sigma that has more sentences, and actually it's going to have more symbols too, so we're going to increase the vocabulary too, that is maximally consistent and contains witnesses, which by the previous video we know that implies that the term model of gamma satisfies all sentences in gamma, and therefore all the ones in sigma. So we need to prove a couple lemmas to prove this thing. So the first one is that if we have sigma and a sentence phi, let's add a sentence phi, let's consider a sentence phi, and we have a constant that is not in any of these sentences. So it's a constant that is completely fresh. It just came out of nothing. It's not being used in any of these sentences. Then if sigma is consistent, so is sigma together with this formula up here. There exists x phi, then exists x, then phi is true when you replace x by c. So we can look at the intuition of this, which is if it's consistent that there exists x phi, and c is a new constant that nobody has said anything about it. Neither sigma nor phi say anything about this constant c. So we can assign c to whoever we want. We assign it to the witness of whoever makes this possible, then this should be true. But this intuition is for satisfiability. This intuition is about if there is a model, we can assign the constant. If we have some model of this, then we should be able to assign the constant to that. That's not what we're doing here, because this is about consistency and it's about formal deductions. So the intuition is just to check that this makes sense, but the proof cannot be through that intuition, because here we have to use formal deductions. So what is the proof of this? The proof is by contrapositive. So suppose that sigma together with there exists x phi imply phi where x is replaced by c is inconsistent. Then by our reduction to absurdum theorem from a few weeks ago, we get that if something is inconsistent, then gamma proves the negation of that something is adding. So we get that sigma proves the negation of there exists x phi implies phi xc. But that is the same thing as just by putting the not inside the implies, so that means that's the same thing as gamma proves that there exists x phi and not phi where x is substituted by c, right? That's just by putting the not inside and, right? This is a tautology essentially. Those two things are the same. And then from there, we get, again, by the T rule, by the tautology rule, if you prove an and, you must prove each of the things, because the conjunction of those two implies a single one. So you get that, well, this proves that x6 x phi and sigma proves not phi xc. Right, and now, let's remember what happens in this case. The constant c doesn't show up in sigma and doesn't show up elsewhere in phi, well, only when you replace x by c. And sigma is still able to prove something about this constant c, so sigma says nothing, has no claim about this constant, says nothing about this constant, but it's still somewhat, it can prove something about it. So what we've seen a couple of weeks ago is that if we have a set of sentences that prove something and this constant c does not show up anywhere else, then gamma can actually show that for every x theta is true. Right, this is what we call generalization of constants, and that's why it's important. It's being used right here. If you prove something about a constant, then you prove this deduction. And this wasn't, it's a proof that had to transform one deduction into the other. I mean, it's still like a manipulation of symbols in this proof, but you can manipulate the symbols in this deduction to build a deduction of this. So we get from here that sigma proves for every x not phi. And we get the contradiction right from here. So let's do one more step. This is the same thing as saying sigma proves not for every x not phi. And now putting these two together, we get that sigma is inconsistent because it proves something and the negation of that something. So we started both from the assumption that this was inconsistent, and we got that this was inconsistent. Therefore, if sigma is consistent, then so is this guy. Okay, and then that's getting closer to what we want about containing witnesses. Let's remind ourselves what containing witnesses means. Containing witnesses says that if you prove that exists x phi, then there exists a term such that you prove phi with x replaced by the term. And now we're saying that if you have this, then you have x a phi with x replaced by the term c. C is a term by itself. Okay, so this is if we want to add one, we want to fix this, find the term witness for this particular phi. We can essentially, the idea is we can add this to it, this formula to it, without losing consistency. So we want to do it all at once. So now let's do the following. For each formula, well-formed formula phi, or sentence is fine, consider a new constant symbol, c sub phi. So c sub phi is a constant symbol. So it's a symbol. It's just a symbol. We're just taking a new one that hasn't been seen before, that doesn't show up in sigma or anywhere. Completely fresh symbol, we just created out of nothing, that we call c sub phi. And we call it c sub phi because we want a different constant symbol for each different phi. So that's why we call it c sub phi. So it's just for each phi, consider a new different constant symbol, we call it c sub phi. Now consider this set of sentences theta. It contains all the sentences of this form. If there exists x phi, then phi holds with x replaced by the constant c sub phi, the one that corresponds to phi. And this is a set. We consider all these formulas for all well-formed formulas phi. Okay, so it's a whole set of formulas, each one using a new constant symbol. Then, if sigma is consistent, then so is sigma union theta. Okay, so theta doesn't break the consistency of sigma. Why is that? Well, I guess we have to assume here that our vocabulary is countable, but sure, it's countable. And then we proved before that if we add these formulas one at a time, we never break consistency, right? So we just added one at a time, and we prove that they're all consistency, so consistent. So maybe if you want to do it formally, this is what the steps that you should take. Start by considering an enumeration of all well-formed formulas. We did this before. If the vocabulary is countable, we have countably many symbols overall. Even though it's infinite, right? We're adding infinitely many constant. Well, these are the vocabulary. This is vocabulary without these new constants. This is before adding the new constants. But still, maybe we had an infinite vocabulary. We definitely have infinitely many variables. Whatever, we have infinitely many formulas, but we can enumerate them. Like in the dictionary, we can fix some ordering that we can enumerate them one at a time and going through all of them. And then we need to use induction to show that for every n in the natural numbers, we have that sigma together with the formulas there exists x phi sub I imply phi sub I where x is replaced by c for I less than n is consistent. Right, but then this one we know is consistent because we know this induction because the induction step is exactly the lemma that we had before. If we add one formula of this form and the constant c is new, and remember we're adding these new constants that are all new and they don't use the previous one. Every time we add a new one, we stay consistent. So we are adding them one time by induction and one at a time, and each time we use this lemma, and we always stay consistent. We started with something consistent and we add more and more and more, we stay consistent. Then when we add them all, why is that we get that it's consistent? Well, if not, if sigma union theta was inconsistent and it proves something of the form beta and not beta, then the proof used only finitely many symbols, right? Finitely many formulas, because the deduction is a finite list of formulas. You can only use finitely many in a deduction, it's just a finite list. So you have to use only finitely many of those. So there exists an n such that this set up here, sigma union this set, proves beta and not beta. But then we know this is consistent, so this cannot be the case, right? So we get that the whole thing must be consistent. So if you're consistent along the way and you're taking a union at the end, you must be consistent at the end. So that's how we can add them all together. We can add all these formulas all together for all sentences now. Formulas, and we add them. Okay, so we add them all like that. And now this guy contains witnesses, right? Because, let's see what that meant again. Contain witnesses that if you prove there exists x phi, then there exists a term such that you prove phi with x replaced by the term. And here, if you add this formula, if sigma proves this guy, we don't know if it does, but if it does prove this guy, then it proves this guy, right? So this one contains witnesses. So one thing to comment here, which I don't want to get too deep into it, but it's important, is that these formulas phi must use these constants c, because we want to consider all formulas in the vocabulary, so we can consider them all, right? So we can write formulas that use other formulas. Well, but let's do it in a way that you never use a constant that haven't been built so far, right? So when we're talking about phi2, you only use constants that appear maybe the one for phi0 and phi1, but not the future ones, right? So every time when you're enumerating these guys, you only use constants for the formulas that show up before. You don't use constants for the ones in the future, right? So we preserve this thing that every time you add a new one, a new of these, the new constant you're adding hasn't been used before, right? So is there not an issue with that, right? So just make sure that when you enumerate all the formulas, you never mention constants that refer to future formulas. You only mention constants that refer to previous formulas. And there's not an issue with that. So then the whole proof goes, and then you get here is all from the formulas, even the ones using these constants. You get this, and therefore this new guy contains term witnesses. Everything of this formula is proof contains a term, and the term is actually a constant. So we can say that it contains constant witnesses, not just terms witnesses. It contains constant witnesses for all existential formulas that it proves. And now, so we're done, because what we know already that if you have a consistent set of formulas, you can extend it to a maximal consistent set of formulas. We did that last week. So whenever something is consistent, you can extend it to a maximal consistent. And we didn't change the vocabulary when we did this. Same vocabulary, we just added more sentences. So if sigma didn't prove a sentence or a negation, we were able to add one of the two, so that stay consistent. So you can always extend something to be maximal. So if you have sigma, we add theta, we make it contain term witnesses, and then we extend it to gamma, that is maximal, the same way we did before, and then that finishes the proof of this theorem, right? So we first add the witnesses, and then we make it maximal, and that theorem then finishes the proof of completeness. because if you're maximally consistent and contain weaknesses, then your third model is a model of you. So there we go. We started with something consistent and we build a model for it. So we made it satisfiable. And that proves completeness for you guys. So that's it. That's the biggest theorem of this class. Pretty important theorem. Let's sum it up in the next video.